Tesla just revealed how zero-defect manufacturing could actually end car repair bills forever. The Model 2 uses 1,800 real-time sensors that catch every misaligned bolt and panel gap before the car leaves the factory. Combined with a 2 million-mile aluminum-ion battery and a single-piece cast body designed to last 30 years, this isn't just another EV. It's a vehicle engineered to never break down. But here's what everyone's asking. Can these zero-defect systems really deliver maintenance-free ownership, or will hidden costs emerge years later? Here's what most people don't realize about car defects. They're not random. Every rattle, every leak, every misaligned door starts as a microscopic error during assembly that compounds over years. Traditional automakers inspect finished cars and hope they caught everything. Tesla flipped this approach completely. The Model 2 production line deploys 1,800 sensors tracking every single assembly step in real time. Each sensor monitors bolt torque, vibration patterns, frame deviation, and panel alignment as robots work. When a bolt gets tightened, the system doesn't just record that it happened, it measures the exact force applied, the position down to micrometers, and any deviation from the program spec. If anything falls outside tolerance, the line either alerts engineers or stops immediately. Defects die at their source, not in your driveway 3 years later. But here's where it gets interesting. Tesla's Vision AI system measures panel gaps with precision most manufacturers can't even test for. Traditional cars accept 2.0 to 2.5 millimeter gaps between body panels. The Model 2 maintains 0.4 to 0.6 millimeter. Why does this matter? Because every gap is a future entry point for water, dust, and the slow degradation that turns new cars into repair nightmares. Tighter gaps mean fewer leaks, less wind noise, and dramatically reduced rust potential over decades. Now, Tesla also implemented something called SPC 2.0, statistical process control that doesn't wait for problems to appear. Instead of inspecting finished vehicles, this system continuously tracks torque readings, equipment temperature, and deviation patterns across the entire production line. If a parameter starts drifting toward its limit, even before crossing into failure territory, engineers get flagged and intervene early. This proactive monitoring has cut post-production defects by 50 to 70% compared to reactive inspection methods. Think about what this means for ownership costs. The majority of warranty claims and early repairs trace back to assembly errors that weren't caught in time. By eliminating these issues before the car ships, Tesla removes the entire category of manufacturing defect failures. But can sensors really catch everything, or are there limits to this approach? Every Model 2 undergoes 100% electrical testing, not sampling, not batch testing, but every single unit. High voltage lines, the 12-volt system, sensors, control modules, all get diagnostic verification inside the factory. Any miswired connector or abnormal signal gets detected before delivery. Then comes the water test. Tesla subjects each Model 2 to the JIS severe rain standard, which simulates 2 hours of heavy downpour across the roof, doors, windows, and every panel gap. Engineers watch for a single droplet entering the cabin. If they see one, the car leaves the main line for correction. This process nearly eliminates interior water intrusion, one of the most frustrating long-term failures owners face. No more mysterious wet carpets or corroded electronics years down the road. Even doors and seats, components that degrade on nearly every aging vehicle, get micrometer scale alignment using specialized robots. The system measures hinge parallelism, opening force, and seat rail torque to prevent the sagging doors and loose seats that plague 10-year-old cars. This is the difference between a door that still closes smoothly after a decade and one that requires lifting just to latch. Battery replacement is the single biggest cost fear for EV buyers. Replacing a battery pack can run $10,000 to $20,000, essentially totaling an otherwise functional vehicle. Tesla's claim that the Model 2's aluminum-ion battery lasts 1 to 2 million miles sounds impossible, until you understand the chemistry behind it. Lithium-ion batteries show noticeable degradation after 1,000 to 2,000 charge cycles. That's why EV batteries lose 10 to 20% capacity within the first 5 years. Aluminum-ion cells operate differently. They can endure 8,000 to 10,000 cycles while preserving most of their original capacity. In real-world terms, if you drive 15,000 miles annually, this battery could last 66 to 133 years before reaching the cycle limits of current lithium packs. The secret lies in the tri-layer mesh anode. During fast charging, ions slam into the anode at high speed, creating enormous internal pressure. Lithium anodes crack and deform under this stress, which is why fast charging degrades batteries faster. The three-mesh layer design flexes slightly and distributes force across a larger surface area, absorbing the impact without structural damage. This allows the Model 2 to fast charge repeatedly without the accelerated degradation that shortens lithium battery life. Temperature resilience adds another dimension. Lithium batteries lose efficiency below freezing and degrade faster in extreme heat. Aluminum-ion cells function across minus 30 degrees Celsius to over 50 degrees Celsius, maintaining performance from Canadian winters to Arizona summers without thermal management penalties. This isn't just about range, it's about longevity. Batteries that don't struggle with temperature don't wear out fighting their environment. Material economics also play a role. Aluminum is the third most abundant element in Earth's crust, far more plentiful than lithium. This stable supply insulates Tesla from the volatile mineral markets that drive lithium prices up and down. For buyers, this translates to a battery that costs less to produce and holds value better over time. Safety offers the final advantage. Thermal runaway, the chain reaction causing battery fires, is lithium-ion's greatest weakness. Aluminum-ion chemistry resists this phenomenon. If a cell fault occurs, it generates mild localized heat and stabilizes instead of escalating into a fire. This fundamentally changes the risk profile of EV ownership and potentially reduces insurance costs over the vehicle's lifespan. But here's the critical question. If this battery technology is so superior, why hasn't anyone else adopted it yet? Is Tesla sitting on a breakthrough, or are there trade-offs we're not seeing? The 50,000-ton single-piece revolution. The Model 2's minimalist exterior hides Tesla's most radical structural innovation, using a 50,000-ton gigapress to cast nearly the entire lower body as a single piece. Traditional vehicle frames contain 300 to 400 welds joining hundreds of metal components. Every weld is a stress concentration point that endures constant twisting forces, road vibration, and temperature cycling. With single-piece casting, the Model 2 needs only about 12 welds. This reduces potential structural failure points by roughly 95%. Think about what this means for long-term durability. Each eliminated weld is one less joint that can loosen, crack, or rust over decades of use. This is why Tesla confidently targets 30-year structural integrity. Torsional rigidity tells the real story. The Model 2 achieves 65,000 to 70,000 Newton meters per degree of twist, about 230% higher than the already stiff Model Y. Higher rigidity means the body flexes less when hitting potholes or rough surfaces. Less flex translates directly to door alignment, window seals, dashboard mounts, and seat rails maintaining their positions for years without developing rattles or misaligned panels. Tesla protects this cast frame with Gigalva Ultra, an advanced anti-corrosion coating engineered to resist rust for 25 to 30 years, even in salt-heavy winter climates. Preventing corrosion isn't cosmetic, it's structural. Rust is the leading cause of frame weakness in aging vehicles, turning solid structures into safety hazards. The single-piece casting also cuts cabin vibration by approximately 28%. Traditional multi-panel bodies have numerous metal joints, and each joint transfers noise and vibration into the passenger compartment. With fewer joints, the Model 2's structure dampens vibration more effectively. Lower vibration means less fatigue on components attached to the frame, hinges, seats, dashboards, electronic modules, all of which last significantly longer when not constantly shaken. Here's the controversial part. This manufacturing approach requires massive upfront investment in gigapress machinery, but dramatically reduces per-unit assembly costs. Traditional automakers can't easily replicate this because their existing production infrastructure becomes obsolete overnight. Is Tesla building a moat that competitors can't cross? Or will this technology eventually spread industry-wide? The parts that quietly drain maintenance budgets aren't high-tech systems. They're small mechanical components that age with normal use. Tesla redesigned these wear-prone parts on the Model 2 to eliminate the gradual degradation that forces garage visits. Suspension bushings in traditional cars use rubber that deforms under compression and twisting, typically needing replacement after tens of thousands of miles. Tesla's elasto-composite suspension structure combines elastic polymers with reinforcing fibers. This hybrid material reduces friction, prevents thermal aging, and allows suspension modules to function for 500,000 to 800,000 miles without bushing replacement. A suspension that durable maintains handling characteristics and prevents the squeaks and vibrations found in aging vehicles. Wheel bearings present another improvement. Standard steel bearings gradually wear from heat and load cycles. The Model 2 uses hybrid ceramic lubricated bearings, pairing ceramic balls with specialized steel races and heat-resistant lubricant. Ceramic balls are lighter, smoother, and resist deformation far better than steel. Their lifespan ranges from 300,000 to 500,000 miles while maintaining smooth rotation and reducing rolling resistance. Door hinges might seem trivial until your car develops sagging doors that won't close properly. Tesla addresses this with an anti-sag alloy tested for 300,000 open-close cycles, maintaining alignment for approximately 30 years of daily use. These hinges ensure Model 2 doors stay tight and smooth throughout the vehicle's lifespan. Here's what all this technology actually means for ownership costs. The average American spends roughly $1,200 annually on vehicle maintenance and repairs, excluding major component replacements. Over 15 years, that's $18,000. Add in potential battery replacement, transmission work, or engine repairs on traditional vehicles, and lifetime maintenance costs can exceed $30,000. If Tesla's zero-defect manufacturing and durable components deliver on their promises, the Model 2 could reduce these costs to near zero for decades. But there's a catch. Complex technology means specialized repairs when things do break. Will independent mechanics be able to service these vehicles? Or does Tesla create a monopoly on maintenance? The answer to whether this car truly ends ownership costs won't come from marketing claims. It'll come from real-world data over the next decade. What do you think happens when these vehicles hit 10 years and 200,000 miles? Will Tesla's engineering hold up, or will new failure modes emerge that we can't predict yet? So here's the answer to whether zero-defect manufacturing can actually end car bills. The technology is real, the engineering is proven, and the economics fundamentally change. When 1,800 sensors eliminate assembly defects, when batteries outlast the chassis, and when structural components are engineered for 3 decades instead of 3 years, maintenance doesn't just get cheaper, it approaches zero. This is exactly why Tesla built the Model 2 this way, to prove that car ownership costs are a manufacturing choice, not an inevitable reality. But here's what matters beyond the single vehicle. If Tesla succeeds, every automaker will be forced to adopt similar zero-defect approaches or risk irrelevance. We're watching the beginning of a fundamental industry shift where durability becomes the primary competitive advantage, not just performance or price. And this is just the starting point. As these manufacturing techniques scale and aluminum-ion battery production ramps up through 2026, we'll see whether Tesla's promises hold at million-unit volumes. The real test comes in 5 years when early Model 2s hit high mileage. What do you think breaks first on these vehicles? The technology Tesla claims is bulletproof, or the traditional components they haven't fully eliminated yet? Drop your prediction below. This is Tesla Zone, and we break down what these technological leaps actually mean for the future of transportation. For the latest on Tesla's manufacturing revolution and what's coming next in 2026, you know where to find us. The age of disposable cars is ending. What replaces it is just getting started.